Okay, good morning. Welcome to the session. I'm Steve Laval. I'm the host or chair for the session. I'm very happy to introduce our first speaker, Professor Nancy Amato from Texas A&M, who will be giving the keynote on sampling-based planning, foundations and applications.
Thanks, Steve. So it's kind of hard to decide what to do with this time, and so I just chose to kind of give an overview of some of the work of my group. So I want to make that clear up front. This is not intended, and I do not cover other people's groups and other groups' work, and there's been a lot of that. But basically, I wanted to kind of make sure that everyone is impressed with what we can do with sampling-based planning. So first off, I hope everyone here is on the same page, but just in case, we're talking about the simplest kind of motion planning problem definition is you have some movable object, you have a description of the environment, and what you want to do is you want to compute a sequence of valid configurations that takes it from your start to the goal. What's shown here is this alpha puzzle example, which has become kind of a benchmark problem for motion planning applications. This is a kind of problem where if you know how to solve it, you know the trick. There's this particular configuration that you need to find. It's right there. Once you do that, the problem's easy. But if you could imagine searching for this just in a sampling-based fashion, that's very difficult to do because there's very few configurations that actually are satisfying that constraint. So what I want to do first is kind of go over a whole bunch of different applications of planning that have been solved by sampling-based planning. Oh, this thing doesn't go away really. So first off, here's an example that comes from intelligent CAD applications. These are problems that both came from General Electric, and they were examples of cases where they came up with a different design, the engineers did, because they weren't able to test things appropriately in the planning phase. And had they had available to them a motion planner that was integrated into their CAD system, they could have come up with a different design. In the one that's actually shown moving, they decided not to actually go with this at all because they weren't sure that it would be possible to actually put the two parts together. And had they had a planner, they could have tested this. On the other one, on the right, is a part of an aircraft engine, and the circled part is a part that needs to be able to be replaced. And you can see that the engineer kind of bent the pipes a little bit to accommodate for what they thought would be the removal path, and it turned out there was a much more simpler removal path that they wouldn't have needed to do, and they could have tested also this had they had a motion planner integrated into the system. If we had a motion planner integrated appropriately into these systems, other things you could do would be training. You could illustrate removal trajectories to engineers or mechanics during the training phase. So there's a lot of things that could be done if we get these systems appropriately integrated. There's a lot of high degree of freedom problems where we have many joints that we can plan with planners. Let's see. If that'll play again. But here you have basically some closed, it's hard to see, but there's 3 series of closed chains that need to be moved together, and this is a difficult problem to plan for. Here we have, so far we just had examples where we had one agent. Here we have multiple agents that need to move and be planned together. On the bottom, we actually have 2 groups of agents. We have one agent who's trying to herd a flock of other agents and trying to push them into this corral type area. The puzzle down there is a disassembly puzzle. That's related to what you would do for a disassembly problem or assembly problem. Frequently, that's one example where we solve essentially the reverse problem. So you start with everything together and you plan to separate them, and you could reverse that to come up with an assembly sequence. Here's an example where the movable object is essentially deformable, and it essentially has an infinite number of degrees of freedom as to how it could be deformed. In this example shown here, that it's the same path that's being followed by the ducky and the teapot, and they are basically deforming to avoid collision with that obstacle there. And there's many different applications for deformable objects. Another one that's a little bit different is applying motion planning to molecules. Here are some examples for protein molecules or RNA molecules. And here, these molecules are also flexible and they can move. The top one is kind of more related. The drug design is more similar to what we think about for traditional motion planning. You have your smaller drug molecule and you need to dock it onto the binding site in the protein. So you could imagine that the drug molecule is your robot, the protein is the obstacle, and you need to fit it into the spot. For the other ones, it's just simply a flexible object, and we need to study and plan for its motions. So those are a bunch of examples of different types of motion planning problems, and we've applied sampling-based planners to all of them. Now, I assume everyone here is familiar with the actual computational complexity of motion planning, but just here's a quick reminder that it's pretty much any problem that we really want to solve is intractable according to the traditional sense of computer science intractability. And so far, the best deterministic planners we have today is still John Canny's planner from his PhD thesis in 1986. And essentially, we can only really apply that to problems that have up to maybe 4 or 5 degrees of freedom. So this means we can't even use it on a rigid body in 3 dimensions. So essentially, we can't really do this except for in most general cases. So what do? We turn to these randomized approaches to try to help us handle the problem, because we still obviously need to solve them. And what this has done is it's led to a whole bunch of different types of methods that have different types of probabilistic guarantees, and they work practically very well in many cases, and we have a major gain in efficiency. So what I want to do now is just kind of give you a quick overview of one of the original ones, which was jointly discovered independently by 2 different groups of researchers. So what I'm citing here is the combined journal paper reporting that. But basically you have, excuse me, configuration space. Here's a cartoon, a 2-dimensional version of that. And the idea here is during pre-processing, we want to build up some, essentially we'll call it a roadmap that includes a bunch of feasible representative pathways that we can later use in solving the query. So this is something that you would use, say, for a multi-query approach. There's also the tree-based methods such as RRT, and today I'm just going to go over the roadmap-based approach. So in the first step, you generate a bunch of configuration samples in your space. You evaluate each one. You discard the invalid ones, the red ones, and you retain the blue ones, the valid ones. Then for each one, you try to connect it to its nearby neighbors. And after you've done that for all of them, you're left with a roadmap. And you do this all in pre-processing without idea of what the query will be. Then later on in query processing, you have your start and your goal configurations. You connect them to your roadmap, this graph, and then you can use your favorite graph search technique to pull out a path. And this was a very revolutionary idea when it came forward, and it allowed us to solve problems that we hadn't been able to solve at all. Many high-dimensional problems. They are probabilistically complete, meaning that is you take as you keep sampling, that eventually the topology of your graph represents the topology of the underlying space, and they support fast queries with enough preprocessing if your graph is well connected. But unfortunately, they didn't solve all the problems, and this little figure here can kind of give you the intuition about what's going on. When you're just taking random samples, most of your random samples are going to be in the places where the space is relatively free, where you don't really need them, honestly, where the planning is easier, and you don't get them in these narrow regions, the so-called narrow passage. And so this kind of gave rise to this problem, which we call the narrow passage problem, which is still a challenging problem for these sampling-based planners. And the problem there is, if you have a really narrow region of your configuration space, how are you going to sample it and ensure that you sample it using these sampling-based methods? And basically, the work of my group and of many other groups working on these problems for the last, decade or so has really been focused on different versions of this narrow passage problem. So I'll just kind of mention a few of these types of sampling-based methods that were developed in my group to try to address this narrow passage problem. And I'll actually show you one or two of these, an example of them. So the very first one was this one we called obstacle-based PRM, and that was trying to sample near the obstacle surfaces. Another one, MAPRM, medial axis PRM. There we were trying to sample on the medial axis of the free space to try to have paths that had higher clearance. A method that we're still working on today, and there'll actually be a paper presented tomorrow by my student, is reachable volume sampling. And the idea there is to try to restrict the sampling to the feasible space in your constraint system. Toggle PRM, that was one where we were trying to simultaneously map both the free and the block space and to use the information of those together to kind of help us map the other space. And another one, FIRM, feedback-based information roadmap. There we were trying to extend the sampling-based strategy to belief space and uncertainty. And then there were some other strategies we were trying to apply to try to do sampling more efficiently in general, and that was to take advantage of parallel processing. You know, this is a hard problem. We have parallel systems all over today, and how can we do that? And then another one, which is repairing approximate paths. That's basically trying to take into account the human insight together with the planner to kind of come up with a hybrid system. So just to give you an idea about this first one, OBPRM, if you're not familiar, is really simple. The idea here is, if we look again at this example, we get many of the samples where we don't really need them, and we don't get them where we need them in those narrow regions. Instead, what we'd really prefer is to get things near the surfaces of these obstacles, because that's where planning is hard. Well, one of the problems is we do not and cannot afford to explicitly construct these configuration space obstacles. So how are we going to sample near them if we don't have any representation of them? On the other hand, we have information that we're not using. We had information related to our workspace, and we weren't really using that in these initial just uniform sampling methods. So here's the idea. It's really simple. If you start off with some point that's basically in collision, select a random direction, and now we're going to essentially do we're going to look for a point that's free in this direction, and now we can do a bisection search. Really, I should have got rid of that. And we'll eventually we do this. Now we can continue, and we do this again and again until we're satisfied that we're close enough to the surface. Kind of one of the unfortunate things about this is it didn't tell us anything about the distribution of the points that we get on the surface, and so that was kind of, you know, theoretically unsatisfying to us. Recently, we have a new method that actually does guarantee that we get uniform distribution on the surfaces, but it turned out to work surprisingly well. This toggle PRM, this one, the idea is you simultaneously map the free and the block space. And when you're taking if you have, when you're trying to make a connection in the block space, say in that red map, and I can't connect the two connected components, well, I've perhaps found a sample that's in the narrow passage, and I can now use that in my building up the map of the free space. And that turned out to work quite well and be essentially kind of insensitive to the narrowness of the passage. So here's an example where we had these three different passages, and obviously the third one is much harder and much narrower than the first one. And the red bar here is showing how many samples we got using the toggle PRM inside the narrow region. And you can see that, and it's versus some of the other ones that were actually kind of built up to try to do this, such as Gaussian sampling, OBPRM, and the bridge test. And you can see that this strategy helped us get a lot of samples in the narrow region better than the other ones. For parallel sampling-based planning, the idea here is pretty simple. We break up our workspace into different regions. We plan independently in each one of those regions and build a roadmap in each region. And then we try to connect them together. And basically what it does, it allows us to kind of limit the communication, which is something that we need to manage well in a parallel method, to trying to just those adjacent regions and not the entire space, which turned out to be one of the issues in scalability of the previous parallel methods. And my former student, Sam Jacobs, who's also here and has a paper here at IROS, did this as part of his thesis work. So here's another thing that I've been thinking about for a long time, and I still haven't figured out the best way to do this, but I think that this is really an important way to go. When we look at this problem here, this flange problem, we know kind of roughly what the trajectory looks like to separate those two. But that's something that's really difficult for these sampling-based planners to try to figure out. So what we did for this is we would have a user use some haptic input device, force feedback device, to essentially kind of collect an approximate trajectory. It's going to have collisions because these problems or these models are very complex, and it's difficult for us to actually have them work and accurately enough so that the user really gets a free one. But it's good enough, it turns out, for the user to collect an approximate one. And the idea here is you can think about it. Suppose the user collects a trajectory that's kind of like that red path. What this can do now is I can now give this to my planner as some approximate method, and the planner can now focus on trying to improve it. What this does for the planner is it greatly restricts the region of the configuration space that the planner needs to search, and so it can make this problem be something that you could solve with a planner. And so you could come up with this blue region here. And here's some kind of results that we got, a long time ago, actually, now. And we applied it to, here's what's shown on the x-axis are 3 different versions of this flange problem. The 0.85 means that we shrunk the inner tube to be 85% of its original size. The 0.95 means it's 95% of its original size, and the 1 means it's the original problem. And the dark blue, or the navy blue, is the results when we used our obstacle-based planner to solve it. The red is when we had the user collect a path, and then we pass it off to the planner, and the planner fixed it. And the yellow one is the one I found most interesting. That's when we took the correct solution path for the previous version of the problem, and we used that as input to the planner for the next version of the problem. And it turned out that's how we were able to solve this original version of that problem. We took the correct version for the 0.95 version of the problem and gave that as input. Unfortunately, this problem here doesn't show my premise that we need the user, because you could have taken the fully automatic method for the first one, the 0.85 version of the problem, and then use that as the solution for the next one and the next one. So which turns out to be an interesting method too. But anyways, I think that there's still a lot here that we need to do, but we don't really know how to do it that well yet. The last thing I wanted to talk to you about is the molecule problems, and this one is a protein folding. And first, I just want to make clear that this is not probably the version of protein folding that you're thinking about, which is where you're trying to do this protein structure prediction. What we were doing, and we're looking at a problem where we actually know already the native structure of the protein, but we're interested on how it may obtain it. And this is important because there's actually a lot of diseases that are related to protein misfolding. So if we can understand more about how proteins fold, we could also understand more about how they may misfold and how we might be able to prevent that. And here's another example where computational techniques are absolutely critical. It's not something you can really study with in experiment. It's difficult to see this happening. So the basic idea here and why these motion planning type methods work well is there's this energy landscape that kind of governs how proteins fold, and the native structure of a protein is thought to be the global minimum of this energy. And so you can think about it as we're using these sampling-based methods to essentially map this whole folding landscape. And it turns out it works quite well. We applied it to some kind of difficult test cases, and because that's one of the challenges also with these methods is how are you going to verify them? And so we needed to have some examples where there is some experiment available to us where we can compare. And it turns out we took these proteins that had slight mutations, and they our results were quite good. So hopefully I have convinced you that there's a diverse set of problems that we can address using these sampling-based methods. Really the key to do that, which I didn't get too much into, is defining appropriately the configuration space and coming up with the validation. So finally, I just want to end with a picture of my students and former students and their students from IROS 2011, because they did all the work, actually. So thank you.
Good morning, and thanks everyone for coming. My name is Gonzalo Ferrer, and I will talk about the work that I've been doing in the Institute of Robotics in Barcelona about robot navigation in urban environments. So one of the objectives of our research line is to deploy robots in urban environments. It happens that people move and walk in these scenarios, and we have developed the tools to predict these trajectories. Now, what we want in this work is to integrate these prediction tools into a navigation scheme. So now I will show you the simulated environment of our planner. We have also implemented it in on a real robot. As you can see in this environment, the green cylinders represent people. And well, since we want to treat these obstacles dynamically, we need another dimension that is time. This is the z-axis. So we calculate robot paths inside this circle, and those are the blue lines. So we calculate several paths. We extend this tree by these goals on the edge of this circle, and what we want is not obtaining the shortest trajectory, but we want to reduce the impact of the robot in this scenario. So that means that we want people not to be threatened by this navigation, but try to minimize it. So as you can see, the minimal cost trajectory calculated is the red line. And well, just to summarize the contributions, we have presented this autonomous navigation in this dynamical environment. We integrated it with prediction tools, but we went one step further, and it's not only integrated with prediction, but we are also doing it in a proactive way. That means that each robot path, each position that we are calculating also changes the whole prediction scheme of all the persons in the ascent. And since there's a lot of time restrictions, I mean, one obstacle is not in the same position at a certain time, and at the time after is not, maybe it's not there, we must consider also kinodynamical constraints of our platform. So this is the general scheme. We have external requirements that are a global planner, and these are our contributions: the proactive planner and the motion prediction that is tightly coupled with the planner. So thank you.
Good morning, everybody. I'm Valerio Digani from University of Modena Reggio Emilia, and my work is an automatic approach for the generation of a roadmap for multi-AGV system. So the typical scenario of my work is that one, so an industrial warehouse where there are a lot of AGVs, and usually these kind of robots are constrained to move on a roadmap. And the problem is that in the current state of the art in the industrial application, that roadmap has to be manually built. And this is very time inefficient and time consuming, of course. So our work is to build a roadmap in an automatic manner. And furthermore, this roadmap has to satisfy some requirements. One of these is, of course, the covering of the free space. To do that, we use medial axis transformation of the free space. And second, the roadmap has to be redundant. And the redundancy is achieved by maximizing the number of paths and roads on the roadmap. And this is an index of quality for the traffic flow in the environment. And third, the roadmap has to the connectivity of the roadmap has to be maximized. The algebraic connectivity is used as heuristic in order to maximize the traffic flow. And this problem is translated in assign a direction to each road on the roadmap. Of course, the roadmap has to be feasible and has to be feasible with respect of the kinematic constraint of the vehicles. So in this case, we use straight lines and Bezier curves to do that. And we compared our roadmap, so a roadmap generated with our approach, with current roadmap used in real industrial plants. And the results are that our roadmap is better in terms of algebraic connectivity of the associated graph and in terms of maximum flow of the graph. So, thank you.
Good morning. This is work by Abbas Sedat, who unfortunately can't be here today, Richard Warren and myself. Looking at the problem of placing a sensor in the environment such that we cover all areas that contain things of interest to us, where things of interest can be, as in this example, the cornfield down there, it can be waterways, it can be natural resources or invasive species, whatever you like. The standard approach to this problem is the lawnmower, which works great. It systematically covers the entire area, and it's guaranteed to converge as long as you have enough time and energy. But if you look at this problem a bit more carefully, then we notice that in a lot of situations, things of interest are not uniformly distributed, but rather come in patches like these fields or lakes and rivers. So we waste a lot of time and energy in the lawnmower by looking at places that are not of interest to us. So we could, in theory, do a lot better if we only look at things that are of interest to us. Obviously, this is a chicken and egg problem because we need to actually sense that something is not of interest to us in order to skip sensing them. So what we propose is to do multi-resolutional sensing. And the insight is that this is actually easy to do for flying and underwater robots because we can simply change the elevation at which they move, thereby increase the field of view. Granted, we lower the resolution, but we can go down again when we find something interesting, decrease the field of view, but increase the resolution. So it's important to point out that this isn't the answer to the whole thing, right? So we don't just do lawnmower at a higher resolution and we're done. So the trick is to figure out when we need to go down and up in this multi-resolutional sensing scheme. And what we propose is to use coverage trees. In particular, in this case, we use quad trees, where the parent node covers 4 times the space of a child node. And the cool thing now is that we can just prune the tree and stop exploring as soon as we find an area that is entirely not interesting to us. And there comes the saving compared to the lawnmower. And as always with trees, we have 3 options. We can do a breadth-first search, we can do a depth-first search, or we can use some sort of heuristic. And if you come to the poster later on, I'll go into the details about the heuristic. For now, I would like to conclude by stating that our method outperforms the lawnmower if the environment is sufficiently patchy. Thank you.
Hi, I'm Teresa Vidal-Calleja from the Center of Autonomous Systems, and I'm going to talk about path planning, considering stability for reconfigurable robots. So they can tip over and they can damage vehicles and environment. So there is a range of applications when we can use this type of vehicles, such as autonomous robots, teleoperated vehicles, and human robot and onboard operators. We propose a probabilistic approach to account for stability when planning with uneven terrains. The stability analysis considers as an input uncertain robot terrain, localization error, and uncertain terrain model. This goes to a robot simulator that provides us with the center of mass and the contact points with the terrain. With this, we calculate the stability. So for the simulator, we use an open dynamics engine that is a physics simulation engine where the terrain is modeled as a 3D meshing and for any given point cloud. This simulator will specify how the robot sits on the terrain in a given configuration. And the projection of the robot's body from the top view will give us a contact point and support polygon. With these contact points and the center of mass, we calculate our stability metrics, a deterministic stability metric that we call the force angle. However, the inputs to the simulators are considered uncertain. So we have a distribution, usually we assume a uniformly distributed pose and map with a given mean and covariance. So their goal is to estimate the force angle at the end. So how do we do that? So from an uncertain input, we propagate uncertainty. And you can use the standard Monte Carlo simulation. In this paper, we propose to accelerate the process using uncentered transform. Then we compute our probabilistic method, our probabilistic metric, that is the cumulative distribution of beta, of this force angle. For the per planner, our stability metric can be applied to any cost-based path planner. And it can be done combining distance, stability, and visibility. We gain more confidence using our probabilistic method than the deterministic force angle or the simple mean. We have results in Rescue Arena and outdoor data sets. Please come to the interaction session.
Hi, everyone. I'm Chris Bowen. I'm presenting my work with Dr. Ron Altrovitz on closed-loop global motion planning for reactive execution of learned tasks. The problem we address is that of executing a task learned from demonstrations. In this example, the robot must scoop powder from a container and transfer it to the green bowl, even if the bowl is moved during execution. Note the spoon remains level to prevent spilling without an explicitly enforced constraint while avoiding obstacles. The powder transfer task was learned from human-guided demonstrations, like the one shown in this video. Task execution in this context poses a number of challenges which have not been addressed together in prior work. First, during execution, we maximize adherence to the learned task. Second, we avoid new obstacles not present in the demonstrations. And finally, we quickly react to the movement of landmarks, like the green bowl. To address the challenge of reacting to the movement of landmarks, we employ a closed loop that repeatedly senses these landmarks and runs the planning algorithm to maximize adherence to the task, conditional on the sensed landmark locations. The task itself is represented by a hidden Markov model, where states correspond to discrete time steps and observations correspond to configurations of the robot. This model can be thought of as a discretization of time in the form of a graph. To address the introduction of novel obstacles, we build our planning algorithm on top of a probabilistic roadmap, which discretizes the free configuration space by randomly sampling configurations which are treated as vertices in a graph, and finding local plans between nearby configurations, which are then treated as edges. We combine the task model and the roadmap by considering the Cartesian product of these graphs. The resulting graph has a vertex for each configuration at each time step, along with appropriate edges. So the task model discretizes time, the roadmap discretizes configuration space, and their product discretizes space-time. Finally, to address the challenge of quickly finding the plan which best adheres to the learned task, we apply a classical bidirectional shortest path search algorithm in parallel to this Cartesian product graph, with a carefully chosen notion of cost. This algorithm proceeds from the start and goal vertices simultaneously to efficiently find the global shortest path. Here's another example execution. Again, the robot successfully accomplishes the task even when the green bowl is moved, despite the presence of obstacles. We've also applied this method to other tasks, so for full details, I hope you'll join me during the poster session. Thank you.
So, hello everyone, I'm Jingru from Indiana University. The work I will present is an empirical study of optimal motion planning. In the beginning, let me ask you a question. So, if you are given an optimal motion planning problem, which planner would you pick? You may say it's an unfair question, because the problems could have many different characteristics, and different planners could be good at solving different ones. The research on optimal motion planning has studied three major approaches: sampling-based, grid-based, and trajectory optimization. While the best performance of each planner, probably after careful problem selection and finite parameter tuning, is reported in the literature individually, few studies have compared the planner performance on an equal footing. Therefore, for the fundamental question, given a class of problems, which planner is the best is still wide open. In this work, we performed a systematic empirical study on optimal motion planning. We considered the kinematically constrained shortest path problems. 6 representative planners are compared on 4 benchmark classes of benchmarking problems. Here are the problems. As you can see, there are narrow passages in each of them, because narrow passages bring challenges for fast motion planning, and we would like to explore how the geometry of the narrow passages would affect the planner performance. We carefully controlled the geometric characteristics of each problem class, including space dimensionality, width, and length of narrow passage, as well as the number of homotopy classes. We considered the 6 representative planners, one from the grid search method, the fast matching method, one from trajectory optimization, cross-entropy randomized planning, and 4 from the sampling-based approach, multiple restore RT with and without shortcut, an RT star, and a lazy version of PRM star. This table lists some high-level conclusions from this study. We obtained some surprising results. For example, fast matching method generally beats other planners for spaces of lower than 6D, and the lazy PRM star performs better as the length of narrow passage increases. Also, we find the hybrid approach, multiple restore RT with shortcut, appears to be most stable. Please come to our poster for more details. Thank you for your attention.
Hi everyone, my name is Nargis and I'm working with Professor Isler in the Robotic Sensor Network Lab at the University of Minnesota. Today I'm going to present our work on the lion and man game on polyhedral surfaces. Now, what's the lion and man game? In this game, we have 2 players, a lion, which is sometimes called as the pursuer, and a man, or the evader. And these players are moving in an environment. In the original setup, they're moving in a circular arena. And they're moving in turns, and in each turn, they have equal speed, and they can observe each other's location. Now, the goal of the lion is to capture the man, while the goal of the man is to avoid being captured by the lion. So this problem has lots of applications in robotics. Search and rescue, security, and surveillance are a few examples of those applications. Now, this problem is being studied extensively in planar environments. For example, in simply connected polygons, we know that we can capture the man with a single lion. And when we add obstacles, we will need more lions. Basically, we will need 3 pursuers to guarantee capture in finite time. But little is known when we go to higher dimensions, polyhedral surfaces in 3D. For example, geodesic terrains that have hills, valleys, and even lakes that can model obstacles on the surface. In this paper, we show that we can capture the evader in finite time on any polyhedral surface. And what makes our problem challenging is the observation that there might be more than a single shortest path on the surface between 2 points because of the hills and valleys, the up and downs. And this makes the problem of designing the strategy and also showing that the strategy achieves capture in finite time, challenging and also interesting. I will be happy to talk about the details of our proposed strategy in the, thank you.
Hi everyone, my name is Wen San. I'm going to present my work on motion planning under uncertainty for medical needle steering using optimization belief space. So we're interested in needle steering for liver biopsy. So we consider a bevel tip steerable needle that you can rotate and insert, and you could also control the curvature using some technique like duty cycling. So the goal is, of course, like insert the needle into the liver tissue while avoiding possible obstacles such as vessels and also rich targets. So the challenge here is that the needle is non-holonomic and under-actuated, and there is motion uncertainty that could be caused by tissue deformation and needle torsion. And there is, of course, sensing uncertainty, which could be caused by partial noisy sensing. So so the goal we wanna consider motion and sensing uncertainty in planning, and we instead of just computing a static trajectory, we want to compute an uncertainty-aware control policy that could be used for closed-loop execution. So the approach is planning belief space, and as you know that we could always using a Bayesian filter to keep tracking the belief, and in our work we using a Gaussian distribution to model the belief states. And so now given the dynamics and sensing model that later could be used to model the belief dynamics, and also the cost functions that could encode things like needle insertion speed, rotation speed, and obstacle avoidance and things like that, the goal is to compute a control policy in belief space. So the dynamics is modeled using extended Kalman filter, assuming that the observation is random. And so now, in terms of the optimization purpose, we use a belief space variant IOQG approach to optimize. So here were some results. We first assuming like 2D sensing model, which could be from an X-ray or ultrasound image. So the local optimal solution really gives us like high probability of success and lower deviations, things like that. So we also applied it to a 3D sensing model. So it shows that it converged from a low quality plan to a local optimal solution. And as you can see in the execution, the robot first guides itself to some high accurate sensing region to reduce the noise, to reduce the uncertainty in the past, and then approach to the goal region. So yeah, I guess that's it. Thank you.
My name is Nicholas Stifler, and I'll be presenting this collaborative work with Jason O'Kane on a sampling-based algorithm for multi-robot visibility-based pursuit evasion. So what exactly is the problem? How can a team of robots guarantee the capture of an arbitrarily fast evader? Well, there's some good news. We have a complete algorithm. This was work presented at ICRA earlier this year. But there's also some bad news. It's impractically slow at this point. So, does sampling help? Our intuition is that, in traditional motion planning, sampling techniques have been able to provide feasible solutions while searching these complex spaces. Here's an example of an RRT, and we saw a PRM earlier in Nancy Amato's talk. But there's a slight complication. The relevant space includes both pursuer configurations and potential hiding places. On the right, you'll see two pursuers, or purple circles, and then these two colored regions of the environment, the green region and the red region, indicating an area where these evaders can be hiding. So the general idea is that we want to sample in the configuration space. You'll see these supernodes outlined by those dashed ovals. Each of the configurations in that space are the same. And the intuition is that we want to be able to track these hiding places indirectly. So you'll see this data structure that is able to connect up these subnodes. And, so, that's not good. So here we have a video of two pursuers moving through the environment. The red oval and the teal oval are pursuers. They have an omnidirectional field of view. The red region is an area of the environment where the pursuers can exist at this point in time. The blue area is a cleared region where we are guaranteed that no evaders can be hiding. And I'll let this play out because obviously the visuals are going to do more than my talking at this point. And you'll see that this problem is often complicated by the fact that we have recontaminations. You'll see some of these blue areas, when they end up merging with a red region, which is contaminated, that they end up making a larger contaminated region. So it could potentially require our pursuers to revisit a place that it had been previously. And thank you. I'd like to talk to you guys more during the poster session, and I'll have other simulations running during that time.
Hi everyone, my name is Tadej Petric. I came from JSI in Slovenia. I'm going to talk about the online learning of task-specific dynamics for the periodic tasks. And I basically decided to show you a video, and then of course if you're interested, please meet me in the interactive session. So basically, the main motivation for our work were how to actually accurately track the desired trajectories while ensuring also the compliant behavior of the robot itself. So of course, in order to achieve both of these two properties, a dynamic models of the task are required. Of course, to obtain these models, there are different ways. One would be, for example, to use just mathematical modeling. But this would not be actually very efficient in practice, especially if we are also considering that the robot should also be used someday with an average user. So therefore, we propose an algorithm which can actually learn both the desired trajectory and task-specific models at once. So the algorithm that we proposed is essentially a multi-step process where in the first step, as you can saw here in this video, a human tutor was actually showing the robot how to, for example, perform a task. For this step, we used adaptive oscillators combined with dynamic movement primitives to extract the desired movement trajectories. Once those trajectories are learned, we move to a second step where those trajectories are used in a way that the robot can learn the proper dynamics. Of course, again, once this dynamics is learned, we can evolve to the last step where both of the trajectories are used in a manner that the robot can afterwards perform the task in a way that it is actually tracking the trajectory and it is compliant. So here on this video, for example, you can see how the robot was able to learn both trajectories as well as the dynamics, and afterwards, when both of the parameters are learned, it can basically successfully perform the task while also being compliant. So being compliant is also one feature that we believe it's quite important because if the robot is compliant while performing this task, it's also more safe to work with humans or in the unstructured environment. Again, if you're interested in this work in more details, please come and visit me during the next interactive session. Thank you.
Hi, hello, good morning, everyone. Today, I'm very happy to give you a talk towards consistent reconstructions of indoor spaces based on 6D RGBD odometry and Kinect fusion. I'm Hai Wei Zhong from University of Ottawa, and co-authors are Nadia and Abdul Muttalib El Sadiq. So actually, in this paper, we improved the Kinect fusion large scale by adding in estimated pose based on both RGB and depth information. Specifically, we propose a 60 RGBD odometry approach that finds a relative camera pose between consecutive RGB frames by key point extraction and feature matching both on the RGB and depth image planes. And furthermore, we feed the estimated plots to the Kinect fusion algorithm. So the yellow blocks highlighted our contribution here. And to validate the capabilities of a proposed algorithm, we conducted our evaluation on the RGBD SLAM dataset and benchmark provided by STEM. As you see, that it includes a Freiburg 1 room and Freiburg 2 desk, 2 sequences, and we compare our results with the publicly available trajectories estimated by King-Fu large scale and RGBD SLAM presented by Andrews. So to show our improvement, you see that the King-Fu large scale, which shows as upper subfigure, fails to incrementally estimate the camera pose due to the planar surfaces of walls and closets, whereas our method shown as the lower subfigure, in combination, King-Fu large scale shows no sign of drift and moreover alleviates the failure from using dense ICP based solely on the depth information. And then next we compare the accuracy. You see the trajectory difference and translational error based on Freiburg 1 room are shown on the right side. And the experimental results, lower 2 figures, show that our proposed reconstruction method outperforms the state-of-art RGBD SLAM system accuracy. And furthermore, we applied both of the data set, and the right figure shows the comparison results of the trajectory errors against the ground truth. The results in bold indicate where our approach outperforms RGB SLAM. And our method finally shows the comparable results with RGB SLAM. And thank you for your attention. I'd like to answer any questions in the following interactive session. Thank you.
Hi, I'm Rev Birkvens, and I want to tell you about the research we've done on biologically inspired SLAM using Wi-Fi. We replaced the camera images used in rat SLAM with Wi-Fi fingerprints and a compass. Additionally, we created a sensor fusion system that, with Wi-Fi and camera, and tested it in a situation where both sensors are complementary. Here, you see rat SLAM using Wi-Fi and compass in action. On the left side, you see how an experience map is created. An experience map is a postgraph of locations. This experiment is done in a university building with a circular shape. We drove 2.5 circles in one direction, after which we made a U-turn and drove again 2.5 circles in the other direction. The total travel distance is about 750 meters. Images taken during the trajectory are shown in the right lower corner. For clarity, these are not used in the algorithm that is currently demonstrated. In the upper right corner, we show the rat SLAM postal network, which receives odometry, Wi-Fi, and compass information and guides the experience map. This is our Wi-Fi fingerprinting approach. Each column of colored disks represents a fingerprint. The color of the disk indicates the received signal strength of a given access point. The position in the column indicates the access point. After driving the full loop of the circular building, the robot reaches a location that it already visited. At that point, the fingerprints will be similar, although not exactly the same, and the algorithm will be able to perform loop closure. These are 3 experience maps created using, from left to right, Wi-Fi, camera, and our sensor fusion system using both Wi-Fi and camera. This run is about 1 kilometer long and is performed once during the day and once at night. It consists of both indoor and outdoor regions. The Wi-Fi algorithm successfully matches day and night runs, but the resulting experience map doesn't quite look like the ground truth. The camera experience map looks more like the ground truth, at least during the day, but it is unable to match day and night runs together. The sensor fusion algorithm allows the experience map to look more like the ground truth and still match the day and night runs together. I will be glad to elaborate on all this during the interactive sessions. Thank you for your time.
Hello everybody, I'm Aravindan. I'm going to present our work on point cloud registration using congruent pyramids. The problem we're trying to solve here is global registration, that is aligning 2 point clouds when there is no initial estimate of the transformation between them. This problem is motivated by applications to large-scale aerial mapping, which is happening at Arizona State University. Typically, we collect data using various aerial platforms like the autonomous helicopter and the AutoKite, and we build 3D models of the terrain below. We're interested in creating data products by merging maps created using these various aerial platforms. And typically, we don't have an initial estimate to register these maps, hence our interest in global registration. Our approach to global registration is to find congruent structures in the source and the target point clouds. And from the corresponding points of these congruent structures, estimate the initial alignment using SVD and then refine it later using algorithm like ICP. Uh, the congruent structure used in our algorithm is a pyramid which consists of a quadrilateral base and an apex. Initially, we estimate the congruent bases in the source and the target point clouds using the 4-point congruent set algorithm. And then we estimate the transformation between these two congruent bases using SVD. Typically in aerial datasets, it is common to find regions with flat topographies. Hence, it is possible to find many false positive quadrilateral base matches. To filter out those false positive bases, we add another point which becomes the apex of the pyramid. Now we have 4 planes which pass through each side of the quadrilateral base and the apex. We call these planes as the base apex planes. We then apply the transformation T to these base apex planes to get a new set of base apex planes in the target. The intersection of these base apex planes in the target gives you a new virtual apex for the pyramid in the target. Let this point be f double dash. We then search for a point f dash which is within the epsilon neighborhood of this virtual apex f double dash. If such a point exists, we know that a congruent pyramid exists. Otherwise, we know that the quadrilateral base match is a false positive and we can discard such matches. Once we have congruent pyramids, we can estimate the initial alignment using the corresponding points using SVD. And then we refine it later using ICP. So this is one result on an aerial data set. Couple of things to notice here is this data set has regions with flat topographies as well as regions with varying curvatures. On the right, you can see the merged map which looks consistent. We tested this algorithm on indoor and typical urban data sets too, and you can see the results here. For any questions, please talk to me during the interactive session. Thank you.
Good morning, everyone. My name is Martin Brandão from Waseda University in Japan, and I'm going to talk to you about the formulation performance of cost curve occupancy grids, which is a method that we propose in this paper. So the problem that we want to deal with is to use occupancy grids with stereo vision. As you know, in stereo vision, you want what you want to do is for each pixel on one image, go along a line on another image and find the pixel that matches it. And you do this by computing a cost for each match hypothesis. So once you find the match, you can estimate the position of that point from the camera. What occupancy grids do is that they divide the space into occupied and free space from these measurements. So this is usually done in a winner-take-all approach. So you find the least cost distance and you discard all other distances and you just increase the probability of the occupation of the grid around this distance, this minimum cost distance. The problem is if this distance is wrong, you're discarding the true distance, which could be in another local minima, for example. However, stereo vision already measures the cost at all disparities, and costs are basically a measure of probability or the likelihood of that match. So what we propose to do is to use these costs themselves to use each cost to compute the occupancy of each cell, and we call this approach cost curve occupancy grids. So in the paper, we show that you can compute the probability of occupation of a cell given the cost curve, and that it depends only on priors of occupancy and visibility of cells, and on a measurement model which measures the probability of measuring a certain cost given that the cell is occupied and visible. This is basically a stereo confidence measure, which is a very active field in computer vision, and for which many models already exist. And in this paper, we compare 2 of them for this application. In the paper, we show that these cost curve occupancy grids can surpass occupancy grids on stereo when you don't use pre-filters, and that these cost curve occupancy grids basically generalize the traditional occupancy grids, so winner-take-all occupancy grids. Then we also evaluate the performance of the method and show that it can achieve higher precision over time and higher robustness to image noise, thanks to the stereo confidence models that we use. And we also comment on different design choices such as hole filling methods and stereo confidence model and the cost function window size. So thank you very much, and please come to the poster.
Good morning, everyone. My name is Grace Tai, and this is a joint work with my advisor, Benjamin Kuipers at the University of Michigan. So back in ICCV 2011, we presented this real-time indoor scene understanding framework for indoor navigating robots. So this framework takes in a stream of image data that is taken from a robot traveling along a hallway. And we use an online efficient process to produce a three-wall model to describe the geometry of the observed environment. A year later, in IROS 2012, we extend this framework to handle environment with more complex structure. For example, environment with multiple hallways connected by several intersections. Our previous work has been focusing on indoor environment with empty and clean environments. So this year at this conference, we extend this framework to handle cluttered indoor environment. So when I say cluttered, I mean they're a part of the environment that cannot be described by a simple floor wall model. So the goal here in this paper is to say, how can we select a model to describe as much observation as possible, but at the same time, we want to keep this model as simple as possible. So to put this all together and to sort of conclude what we present in this paper, that is, we take a stream of RGBD images and use an online efficient process with no prior training knowledge, and we can produce a 3D interpretation of the indoor environment in terms of a simple floor wall model and identify part of the environment that cannot be described by the model, and we represent it as point cloud, and we call them cluster. And at the same time, we also identify the robot pose with respect to the model. So if you want to learn more detail about this work or our research in general, please come to our poster section. Thank you.
Hi, my name is Zhang Wang from KTH. The work I'm going to talk about is the modeling of motion patterns of dynamic objects. So we are interested in the long-term moving tendencies. For example, in this corridor environment, for people exiting a certain room, where do they normally go? The difficulty of this research comes from the ever-changing nature of the dynamics. For example, during lunch hours, the frequency of entering the kitchen will be notably higher than other times. This requires the model to be inhomogeneous. We notice that objects move in a continuous manner. That means in the occupancy grid map that we are using, before the current cell becomes occupied, some of its neighbor cells will became occupied first. So we believe that this spatial temporal correlation is a key to model this dynamics. For each cell, we use the input-output HMM to capture these correlations. The input is the observation in the neighbor cells at the previous time step. So essentially, we are using events happening in the neighbor cells as external information to make the current HMM ready for the upcoming transitions. Typically, in conventional HMM, the transition probabilities are fixed. But in our model, they are changing according to the value of the input. So this means that our model provides richer expression power for accommodating the inhomogeneous dynamics. This shows that our model performs better. Our model performs better in the occupancy estimation. Learning from 10 hours of laser scans, we achieved this overall transition model for the corridor environment. The length of arrows represents the transition tendencies from one cell to its neighbor cell. And this cell reflects how people move in this corridor. And knowledge of this cell enables inferring about future trajectories. Thank you very much for your attention.
Okay, hello everybody. So my name is Romain Droguy. I'm a PhD student at INRIA in France, and I also work for ECA Robotics. And I will present you my work on fast hybrid relocation in large-scale metric, topologic, and semantic maps. So basically the problem we address is to know how to efficiently relocalize in large-scale outdoor environments using semantics. So this is a challenging task because we have huge maps and we need for an efficient search lightweight models of the environment. So in this paper, our contribution is twofold. First, we propose a new compact representation of the environment, and then we propose an efficient search algorithm to look for content within the map. So our map consists of a set of local ego-centered spherical views of the environment. These views are built with a multi-camera system. You can see on the picture one. The system has been designed at INRIA. And each spherical views is fully annotated using a random forest and a conditional random field. And then from this labeled image, we extract a semantic graph. That's a graph of the object present in the scene and whose edges correspond to the relationship between the object, as you see it in the image. So this is a 2D representation of the world. And the localization occurs in a two-step process. First, given an image, we extract the semantic graph of the scene, and we look in the map for similar content. For example, where we find the same number of instances of each classes, and then we compare the current semantic graph with the subset of semantic submaps selected. Using an interpretation tree, so we first compare the nodes one by one, and then we take into account the neighborhoods of the nodes to correct the appearance. So finally, we compare our results with standard state-of-the-art bag-of-word methods, and we have very good results. For example, for relocation time, we are 10 times faster than bag-of-word methods. We also have the ability to use complex queries, human-like and human understandable queries. We also are able to manage dynamic object as we know the class of the object we observe, and our representation is more discriminative than the bag-of-word methods. So thank you for your attention. If you have any question, see you in the interactive session.
Okay, good morning, everyone. My name is Raresh Amrush. I'm a PhD student at KTH, and the title of my presentation is Meta Rooms, Building and Maintaining Long-Term Spatial Models in a Dynamic World. The context behind this work is long-term autonomy in human populated environments, and what we're interested in is understanding how space changes with time. In particular, in this paper, we focused on separating the static from the dynamic parts of the environment. The requirements for this work are a mobile robot equipped with a pan-tilt unit and an RGBD camera. And in our setup, the robot conducts autonomous patrol runs in our office environment. So you can see over here in this picture what our app looks like. And the red dots signify waypoints that the robot visits during each one of these autonomous patrol runs. So after reaching a waypoint, the robot conducts a pan-tilt sweep, and we take data from the RGBD sensor and we register it to form this 360-degree point cloud, which we call an observation, and it's the input data for our algorithm. Now, given a set of these observations collected at a particular waypoint, we define the meta room entity, which is the static structure of the environment at that waypoint, and we create one such entity for each waypoint in the patrol run. Once we've created the meta room, we can use it to easily extract dynamic elements from subsequent observations. And I'll talk more about how we create this and some of the properties of our algorithm during the poster session. This shows some of the results that we get using this technique. So the clusters in red represent dynamic objects that we identify in the environment, and the blue points represent the static structure. And taking a closer look at these dynamic clusters, we see that they correspond to objects that you normally find in office environments, such as chairs, people on chairs, lamps, baskets, backpacks, and so on. We've also implemented a simple matching algorithm for these clusters that takes into account a few very simple features, such as the size of the point cloud and the height from the ground. And in this picture, you can see how the position of a cluster corresponding to a chair changes over the week when we collected this data. For future work, we would like to look more closely at these clusters and see if we can use these partial views to reconstruct complete object models, or whether we can build spatial likelihoods of where they're likely to be at different points in time. And this will allow us to, for example, do anomaly detection or improve localization in some situations. Thank you.
Hi, my name is Christoph Brandt. Me and my colleagues are with the Institute of Robotics and Mechatronics from the German Aerospace Center. So we developed a stereo vision-based obstacle mapping for structured indoor as well as unstructured outdoor environments that can be used for fast local obstacle avoidance, as well as, oh, I see, it's not working. Okay, now it's working. So this is a demo we had on the Berlin Air Show this year. So the rover is navigating autonomously in an unknown environment. So only the goal point is given, and all the computation is done on board. So we mainly consider GPS-denied environments. So for the perception of the environment, we use a stereo camera system. And for the pose estimation, we use a data fusion of stereo odometry and an inertial measurement unit. So we generate local obstacle maps, including negative edges, as shown here. So, and we estimate the stereo error. So we believe that the arrangement of obstacles in a local map are suitable to yield robust features for the matching steps performed in a SLAM algorithm, as they are invariant to changes in viewpoint and light conditions. So we tested our system in different environments. So one is our outdoor test bed, shown here in aerial image. So we have several types of gravel, and as well as large rocks and a crater. So for the ground truths, we used a tachymeter for the tracking, and this is the blue line. The green line is the sequentially logged SLAM positions. It's working now. On this slide, the red pass is the pose estimation. So in this case, we had a driven distance of about 255 meters, and the final position error 2D was about 15 centimeters that we achieved. And on this slide are the resulting 2D grid maps of two other environments we tested the system on. So above is an indoor environment with rooms and hallways of a lab environment. So the driven distance here was about 108 meters, and the final 2D position error was about 6 centimeters. And below is a mixed indoor and outdoor environment, so including a loop around the building, and there was a driven distance about 220 meters, and the final 2D position error was about 5 centimeters. So thank you very much.
Good morning. My name is Gershon Parent. I'm from Microsoft Robotics, and I'm going to talk about the benchmark for robotic indoor navigation. As a developer of an indoor navigation system, I'm interested in quantitatively how my system is going to behave in dynamic real-world situations. I want to know how my system compares to others being developed on other platforms in other parts of the world. And I want to see how my system improves over time. But I need to do this quantitatively. The problem, of course, is how can I compare my system running in my environment on different robots in different locations and at different times. And I'm basically primarily interested in typical human environments like office buildings, homes, schools, hospitals, things like that, where there's going to be a lot of dynamic change, a lot of moving furniture, moving people. I want to do this without data sets. So data sets are great for development time, but of course they're canned, they don't change, and I can't really be responsive to how humans might interact with the robot. And I also want to do this without simulations. Without simulations. Simulations, again, they're great, but when it comes to a real-world robot working in a real environment, there's no comparison. So the benchmark defines a diverse but flexible environment specification. I'll show examples of that. And it also has a complete set of environment dynamics. So what's going to change, and when is it going to change, and how is it going to change? As well as a common set of realistic challenges. So encounters with people, encounters with furniture, with doors, and things like that. And importantly, there's a reference navigation system that I'm going to use to create a baseline against which I can compare my results to someone else's results in another part of the world in their own environment. Even if their environment isn't the same as mine, by running the reference platform in their environment, I can gauge and create a baseline against which I can compare my results. Here's an example of a real environment. So you could take something like a building and scope out where you might have an office environment, a lounge, an atrium, a hallway, have them connected in the right way, and be able to combine them. This is these are pictures from that environment, and it prescribes how dense the furniture is, how long the hallways are, and things like that. A synthetic environment like this was developed by the University of Freiburg, where they built it in a warehouse. So you can do that same kind of thing without necessarily having a fixed environment. And this is a synthetic environment that we're going to create here at IROS on Thursday in the expo hall, and we're going to have teams from around the world compete in a benchmark-like competition using the same technology. We also have obstacles defined, we have different kinds of challenges, appearance, geometry, etc. And we also prescribe the test plan, and we normalize the results, and we have a ground truth system, an optical system that looks at the ceiling that measures the exact positions. That's it.